All right, let's start our Warsaw.AI meetup, episode 31. Hi, everyone. Thanks for coming. My name is Paweł. I will be the host of this meetup. And it's formally organized by Fundacja Quantum AI. It's a nonprofit organization that I founded a few years ago. And of course, we are supported by our great partners and sponsors, Allegro Tech. For the next time, we are very happy that we can organize this meetup here. Ideas Research Institute, No Magic Data Art, and we have a new strategic partner, new sponsor, Vecten, formerly Sun Scrapers. We also have representatives of Vecten with us, so we can meet them during this meetup. The plan for today will start from the talk given by Paweł Młyniec from Allegro. Unfortunately, Alexandra is sick, so she will not be able to join us. But Paweł will give a talk on behalf of the team. The title is Lord of the Recommendation Models to Tower for Allegro. And later, Bartosz Naskręcki will give a talk about the revolution of formal reasoning with AI. Thanks, Bartosz. And unfortunately, Maciej got sick as well, so he will not join us. The plan was that he will give a talk about VLM-based solutions in the radiologist practice, but hopefully we'll manage to organize his talk in one of our next events. We hope that you will stay with us for the after party. There will be sushi, as always. Yes, we'll have time until 9 p.m. And there are some gadgets for you, some surprise gifts. Piotr from our team is working on preparing the gadgets for you. So please stay with us until the end and you will get some gifts. All right, so we can start the first talk. So please welcome our first speaker, Paweł Młyniec from Allegro, from our host.
Okay, so hello everyone, and today on behalf of my team and Ola, which is sick, I will talk about recommendation models and especially about two-tower models, which we have on production in many places and how to scale them for different scenarios. And we'll talk a little bit about recommendation one-on-one to be on the same page. Then we'll go through the Allegro use cases, so how we use recommendations. And we'll wrap up with some results from our A/B test. How do they behave on production and on Allegro? A whole talk is based on paper, which was accepted last year to the Rexis conference, and with some updates to our recent this year paper, which is still not accepted because we are waiting, I think, 1 week for that. And to begin with, what is recommendation system? When on the left you have some definition, but to have some intuition, it is some connection between the state or the context to the items we want to recommend. So, for example, if we watch some movie, we want to recommend you some similar movies which you may also like. Or if you have some profile, for example, on the Spotify knows some features about you, and to that user we can recommend different songs or albums. And on Allegro, we have plenty of different scenarios on the user journey. So if you go to the main page, we can recommend you something trending, some trending offers which are right now hot topics. Then if you will search for something, we will recommend you similar items to the whole listing, then because you may not found what you needed already. Or if you are already on some page of the product, maybe it has some not that well features that you might want something bigger, something different from different producent, then we'll recommend you some similar offers or some bundles to actually help you create a basket you want to have. And if you add it to cart, there's like those magical number 45 for Allegro Smart and free delivery, will like help you get those number with some other complementary items which you may like. If you will buy something, well, you can also get something, oops, I didn't know that I need that. I forgot to buy something which is recurrently bought. So there's recommendation of recurrent products. And you also always can buy and recommend something more to those 45 zlotys of Smart. And after purchase, your journey may not end here because you may want to buy something different. So we want to redirect your attention to some other scenarios, products, or other placements on Allegro. So we have different recommendation carousels. And summing those up, we have different scenarios and purposes. We have navigational purpose of the recommendation models. You may want to have some comparison between different products. You may want to get inspired and you don't know what to buy, so you go to the Allegro. And basically, the recommendation carousels are viewed more than 250 billion times yearly, so a lot of times. And we have different recommendation scenarios in number of over 100, so 100 different use cases for recommendation models and recommendation placements. And how it looks like more technically. So we have catalog of products, which we have over there some millions of products, and we want to filter that out to some dozens to which you might be interested with. And we do that with two steps. So first of all, there's retrieval. We want to find some set of items in hundreds, which are the model is lightweight, and we'll use recall for that. And we have some sorting, so actually having the best items for you. This is a little bit higher and higher with a number of parameters model and more complicated, and we'll have NDCG for that. But today we'll focus on the retrieval part. Yeah. I think questions in the end, if you can, maybe there will be everything organized more. And a little bit one-on-one on recommendation model will work in embedding space. So the space, latent space, in which similar items will be close to each other and different items will be far from each other. To do so, we'll have some distance between items. We'll have some scoring to think about how similar items will be. And afterwards, we'll retrieve just closest neighborhood. So for one item, we'll look around these items to get neighbors for that. And with that definition, we can solve almost any problem of recommendation tasks. And first of the problems will be similarity problem. So we want to have something similar. And how to achieve that? So what we do at Allegro is two-tower architecture, which is consisting on two towers already in the title. Left tower will be query tower, so something with what we are asking our index, so how to embed and how to ask. And we'll have on the right the target tower, which we will use to actually think about what we want to find. The training objective is similarity because we want to have similar items next to each other. We'll use some offer features and we'll use user data to have some real world examples and knowledge. And below that, there is multi-layer perceptron. It's kind of simple architecture, but it's really fast, very scalable. It's easy to deploy and maintain for us, because we have 40 milliseconds per whole recommendation, so it has to be very, very fast, with some normalization and other stuff as well. And how we do the training? Well, given those two towers, let's start from the query tower. And the query could be offer, or more advanced, it could be user, or also could be some session. And this is the context that we have. And what we want to find and want to model also as well is some target, and this will be always the offer because we want to receive from our catalog the offers. During training, we are training on the pairwise training, so we'll have what the user bought or clicked first and what he clicked or bought later, so to have some consequences in time. Also, if you notice, the two towers are quite similar, so actually they can share the weights. So underneath is the same one model with the same weights, so it's symmetrical, it's easier to actually optimize, and it's faster to maintain and deploy and infer. Afterwards, there is similarity function, which is .product, which actually tells how close those two embeddings are. And in the end, this is the most basic architecture. At Allegro, we use the sessions, so a little bit more advanced than only offers. And we take them from the user data, we take them from last year of user data, and have a lot of more different training sets objectives, but I won't talk about them right now. And recommendation task can be defined as classification problem with softmax function, which is actually like probability of having some candidate item given the query item. We'll have some embedding, we'll have scoring function, so similarity function of two embeddings, and we'll have some set. So we'll try to find items from the set of items, which over here in this definition is million of products. And to optimize that as classification problems, we'll use negative log likelihood, which is well-known a loss function for that, for observe user clicks. And like some tweak to that, because, well, actually, if you want to scale over millions of items during training, it's not possible right now. So there's like small change to that. So there is negative sampling. So we, instead of taking millions of products, we take thousands of products in one batch, and we try to get those items from that batch, which is already feasible. And this was the first problem. Second one will be complementary recommendations. This is a little bit different, and to explain you why it's different, I will use this example. Instead of recommending something similar, we want to recommend you something complementary. So for example, for one bike, we want to recommend some set of accessories, some safety gear, something you may also like, and it's not a bike because you already have a bike. And there are like some challenges to move from similarity recommendation to the complementary. So first of all, we need to move from substitutes to complementary items. And we, assuming the same embedding space, we want to move further. We don't want to have the same items, but similar a little bit further in this space. To do so, we'll use categories on Allegro, because every product has some category. There are a lot of teams having assigning those products to the categories. It is well maintained taxonomy. So we can use that, and it's already there. For that, we'll use a little bit new deep learning adapter. So we'll use category adapter with some, of course, loss. But as well, we will use categories on production, which we don't know, because we don't know in which categories we want to search. So we'll have some mapping, we'll have some target categories, which were used, created with user signals, annotation team, and also some experts. So it's like predefined target categories. I will explain in next slides. But first of all, how the architecture changed. So there's like almost the same two-tower architecture with some small change on the left. So there is category adapter with inputting the target category. Then we'll like embed this category, add it to the query embedding, go through the fully connected layer to have some mapping to same space as the target offer. And in the end, we'll receive well-known similarity score to retrieve our items from the index. It's and also, like going back during training, there is some new loss, so we have to update the loss because we have new component, and there is loss which is right now composed of two elements. So first is what was already before, so it's two-tower loss, and there is difference between actual category and predicted category. So it's kind of how far away from one category to another our model went with the prediction. And now a little bit those target categories. So how far to move from one item, so from that bike to different accessories, or how far to in which categories retrieve. So for coffee machine, we will like to get some coffee beans, cups, for example, and milk. And well, we don't have this on inference by default, and we have to create those. And what we did at first, we get from the user data. There are like co-purchased heuristics, so user bought this and this and this, but this was super noisy and actually was not that well defined. So we add some human in the loop with annotations. There were like multiple examples and they were annotated by annotators. Afterwards, we employed LLM to actually also score other connections. And in the end, we also ask our experts at Allegro because they do know what is complement to each other in terms of category. And they created some rules to help us actually define those good category mappings. And summing up this part, well, it's actually very similar architecture and components as the previous one, but we changed just one model. We use the same index, ANN index, and now with this change, we actually change the task. And if you already see, there's like also third route on this, and this inspirational recommendations. And to explain what it is, there are like those recommendations are on homepage, so the user doesn't know what he likes, maybe want to expand his bubble, and those recommendations has to be a little bit diverse, but also like relevant to the users. They have to move him outside like what he already knows, and as well like for the maintenance cost, because we have a lot of scenarios, we have to reuse some infrastructure for that. And for the personalization, we'll use user topics from the user history. We'll use multi-vector retrieval. We'll use some tweak to the index and have some hierarchy over there. And we'll reuse similarity to tower model for reusability. And how the topics looks like. So first of all, we take user history. He may bought some items from that. And we'll like assign each topic to each product he already bought. As you see, like there are some repetitiveness in these topics. So we'll like group those topics together. And for each topic, we'll retrieve different items. So in this example, we have 3 different retrievals, 3 different recommendations for that user. And through those recommendations, we'll combine them in one carousel, one infinite feed, which is a little bit more diverse than normal recommendation. And how the index is built, because it's built a little bit different. And it's built with clustering the embeddings together, because we want to have go a little bit further than usual. And it's done with k-means clustering. Then for each cluster, we have some centroid to like help us doing inference time, not to retrieve all items all together. And during retrieval, we take one item and we find the closest clusters to this item, and then we retrieve items from this cluster. So summing up, we have same similarity to tower model as before, but we changed index. We used queries, which was the aggregated user history. We used k-means clustering for the index, and we did some interleaving for to increase the diversity in results. A little bit what changed, because this solution got a lot of different problems. So it was hard to add new features to that, because we don't know actually how k-means will cluster those items. We need to cluster it every day, because at Allegro the catalog changes every day, and it was very, very costly. And we had small control over what is the result and how the result looks like. So we had to change that solution a little bit, and we used our complementary model. Like everything is almost the same, but the target categories, so category mapping changed, and it changed with some external knowledge. And probably, as you may already know, external knowledge right now means LLMs and agentic solution. So there were multiple agents. Some of them were creating some topics. There were then assigning some category to those topics and trying to think about what are good categories for that. Also like how to format, how to score those solutions, how to score those mapping and get the best desired output format. Of course, there are some challenges like with LLMs, so there are hallucinations, happened all the time. So we had to use RAG and search for the real categories and try to always anchor the answers in the real world examples. We want to somehow have connection between those categories. So it was a lot of different tries and errors to get that. There were like automated prompt tuning, which didn't work out that well. There was like manual thinking, and we have to also find some repetitive categories. So actually look into the data, what is a typical error of the LLM and fix that all the time. And all of that was used with LLM as a judge, some experts, and human in the loop. And summing up everything, we have one infrastructure which actually works well for all the scenarios. There are like 3 main use cases, but they do scale for different scenarios. So it's very hard to maintain all of that. And what we have right now is very scalable, feasible for the production. And talking about production, A/B testing those solutions worked out really great. We got more clicks on Allegro, more GMV. We scaled to 20 million active buyers and have more than 300 million products. We have 40 milliseconds for latency, so it's very, very little. And of course, we have different views. So for inspirational, we got tested carousels, so vertically looking at items or just scrolling always infinitely. And it worked out very, very well, like looking like 4%. Probably it doesn't mean anything to you, but for us, it means a lot. And summing up, we have paper. You can already look for the paper for the peer review. It's for Rexis 2026. We got paper from the last year, which you can also look for. And there is Allegro Tech website, which you can also visit. And do you have any questions?
Great. Thank you, Paweł, for this talk. All right, it's time for questions. Bartosz.
I have a few, but maybe I'll just ask one. So I was curious, so you showed us this infrastructure in which you basically make these embeddings, and they are like basically, if I understand correctly, custom-made models for your pipeline. But you have situations like I can imagine you have a product that looks like a Chihuahua, but it's a toy, right? And then you have actually, I don't know, someone who owns a real Chihuahua. And how do you deal with this kind of situations that someone is looking for the context in which some of the products might kind of look like very in the query, like very suggestively similar to what they are asking for, but somehow you'll need definitely something like a transformer, especially like multimodal transformer to figure out that the context of this particular product might be not exactly relevant to the request of the user. Did you notice this kind of situations? It's probably a few percent, but maybe I'm just curious, how do you handle with this kind of odd-looking requests that might be a little bit off the standard pool in which people are usually asking about?
So first of all, it's recommendations. So they're not looking for a direct product. They're products which are similar to product they already are seeing, and how to differ those products. So we use different features, and usually it works out pretty well. So there is title of the product. So usually in the title there is something. If the title is misleading, there is also a category. And now we have a lot of people assigning products to the correct category. And if the product is not in the correct category, it's their problem, to be honest. And some people, some quality assurance at Allegro just is looking for those products to fix those. As well, there's price, which actually, if the product is off, probably is also off by the price. So if there is different price, I think our model already knows that it's a little bit different item.
So you're not doing a lot of exploration. It's more like exploitation of the features that have been already used. If I can get it right.
Yes, we don't use that many features because it has to be lightweight.
Okay.
if we are experimenting with more and more, but it's hard to get those 40 milliseconds for everything. So for the request, calculation, model, and returning back.
Yeah, you said you have 300 million products?
Yes.
Wow. Okay, that's a lot. Okay, thanks.
All right, you have more questions?
Yeah. I have a question because multiple times you mentioned latency and you said it's very important. So I'm curious how sensitive latency to your conversion rates.
Well, I think there are multiple aspects over here, because with all A/B tests, we actually measure latency, and we see that if there's some recommendation carousels are loading too slow, actually user loses his interest. Also, we have the latency limit is from the above, because sometimes there's timeouts. There are requirements from the business that it has to be within this limit, and it's also, I think, there are user experience tests, how long they can actually endure, looking at the loading carousels. So it's also it was also asked users how long it can be.
Yeah, I've got just a simple question. Which model you used for embeddings?
Okay, so it's custom embedding, so it's custom model, and we use multi-layer perceptron. In some use cases, we have also simple transformer. They're more when we care more about consequence in times. So I think there are those two family of models.
Okay.
And I have questions because when you are recommending an item, you are also influencing the user because it is more likely to click on that. And I'm wondering if you have any specific measures to deal with this self-fulfilling prophecy.
Well, actually, it's our main goal to influence the user. The metrics we use, there are multiple. First of all, it's GMV of the user, so of the whole carousels. So it's aggregating all money spent on Allegro. And during A/B test, if the new carousel is better, for example, it generates more money simply. But also we have some clicks, some add to carts, some user actions on every carousel. So we are measuring how much user interacts with the placement, actually.
Right, thank you.
Thank you for the talk. It might be a stupid one because I missed some part of the presentation and it will consist from two parts. The first one, you mentioned that towers are such similar that you can do a lot of stuff with them, like transfer the knowledge and so on. And then the question, why do you have two towers? Why not having one? And I believe you have a good reason for that. Then the next one will be, why not three?
Mm-hmm. So actually it's one tower because they are the same weights, but we use I think I will re-click to that. Yeah. So actually it's Siemens neural networks, so they have the same weights, and we take the same model, we go through with session user or anything query through it, and we go as well with the target. So it's same model used twice, let's say. And why not three? Because actually, if we don't use two, why use three? And it's easier to use one. As well, third tower could be for some different use cases, for some different modeling. We do have third offers usually, but there are negative sampling. So we want to, maybe I will, for that. So for that, during training, we actually take three or even more. So we take those two similar items and we take third item, which is far away. So we include this information, but it's only in the loss of the retrieval. So there's no need, I think, for the third tower.
Do you also take into account how highly rated an item is? For example, does it have a lot of good reviews or a lot of people buy this item? Do you take that into account?
Actually not, because we care more about what is relevant each to another, and somehow we take it, but we take that by popularity. So how much this item was bought with another item. So we don't care that much about rating, but about popularity of the item. And if the item is bought more times, is more popular, it's more times in the training data set, so it's more likely to be recommended in the end.
Hey, I have a question. Actually, it's kind of the, let's say, continuation of the previous question. So I know that this two towers usually struggles with the initialization at the very beginning. So do you take into account, like, how do you solve the issue with the new user, essentially someone with no sessions, no history? Do you have some kind of a, let's say, I don't know, like some starting point for that?
Well, it depends on the placement, because on different placements we have different objectives. So maybe over here. So for example, on the homepage, it's recommending to the user history, and if we don't have user history, our best guess is trending offers. So the offers which are popular right now. On other, we have some context of the user, which is probably over here. And right now, if he goes to some product, it's already his context. So we already know what he's looking at, so we have some information about that. And like in other cases, it's also like what he does right now. So we start to know what he actually wants.
Yeah, I was curious because you probably tested the open weight models like DeepSeek on the product recommendations. Do you see any kind of biases when these kind of models, which were pre-trained in the way that we have no idea how they were trained, like, are they like really biased towards, I don't know, like suggesting products that are like related to China or whatever? Like, have you seen anything like this?
Well, at Allegro, we use mostly Gemini models, to be honest. There are sometimes biased, and well, it depends also on the task, because in the recommendation model, 40 milliseconds is way too low for the like real LLMs.
No, I understand it, but I was just curious, like if you really see that the
in other tasks.
Yeah.
So like it's usually not biased toward Chinese, because it doesn't know what Chinese is, or like for Gemini, it doesn't know what American is, to be honest. It's totally biased towards some predictions. So like with creating of the, that's a lot of clicking, but with creating some mapping with LLM, it actually like was always recommending Bluetooth speakers to everything. It was always recommended blankets to have like cozy evening. It was like, I think 50% or maybe less of recommended categories. And well, we had to like find it actually and do some qualitative and quantitative evaluation of those creations of LLM and fight it back. So
I'm just curious, like, do you do some kind of adversarial training? Because like probably a lot of your users are going to ask other models, especially like ChatGPT or whatever, for recommendations about what to buy. And I guess you should probably kind of align with this kind of ideas that they might have, right? I mean, they will be biased already in the first place when they'll be asking for the products, right?
Well, yes. And that's, I think, a little bit different topic, because if already user knows what he wants to have from Allegro, he will use search probably. So he'll type query and text query, and then there's like listening, and it's completely different model and completely different flow. And then we are just like assuming that other users also, given this query, also want that product. So it's like a little bit population knowledge, let's say. About like having one item and others, well, we do what we can. We like not aligning with LLMs because they change too often, to be honest. We just trust our users and what they do on the platform.
So you're saying cozy means blanket. That's nice.
Yeah, kind of.
Okay, thanks.
Okay, thank you. Well, I'm not sure. Probably I will go beyond the scope of the presentation, but someone already has hinted on the problem. building, because I imagine your system works very well within the platform on the data that is available within the platform. But what about building the context from other sources that may be matched to your data? And certainly it was hinted that probably cold start problem where the social login scope harvesting is the simplest tool to begin with to improve the recommendation system on a given platform. But the question is, have you thought about building the context from other sources? Maybe not necessarily needing the identity resolution layer, but at least such simple things like, for instance, the API weather that suggests to people that you have to buy umbrella if it is raining tomorrow. And the question connected to this question, in such a case, if you have tried to add data from other sources than your platform, how do you navigate the very thin path between the technical possibilities, technical architecture, and legal constraints? Thank you.
So answering first question, actually, yes, on Allegro, we do take external data, but it's not about user, it's about like commonly known data. So for example, like knowledge, what is trendy, calendar, etc. And we take this data to recommend things on the homepage. So if there are trending, we are looking what is trending right now. So for example, is it wedding season, or is it some, I don't know, is there any concert nearby? And we take that, but it's completely different kind of recommendation for that, because it's not taking user as an input, it's taking like the external knowledge, and all of that is like digested through the LLM, to be honest. And about some legal constraints, well, yes, if we take user data, we take only for Allegro, from Allegro user data, we have to be consent with CDPR. So it's like always the legal problem, and we ask our legal team like how to do that, how to store that, and all of that. And yeah, we don't take external user data. It's also like there were some tries, but you have to pay for that. It's kind of noisy, and that's a lot of work.
I'm a big fan of Allegro. I still think this is one of the greatest retail platform all around the world. So thank you very much. And I got a question. Do you have any cool insights about like how do you tackle the problem of the cold start? Like, or is it outside of the scope of your job and this speech? Thank you.
Well, I think there are like two different kinds of cold start, because there could be new item to Allegro and there could be new user to Allegro. So for the new user, we take what is popular overall with the users. So if like, I don't know, 200 million users are browsing for some coffee, well, let's recommend this coffee. Maybe he will also like it. And for the products which are new to Allegro, it's solved by having those features from this product. So if we have some features already, we can actually digest it through our recommendation system, because it can be embedded with that.
All right, good. Yeah, follow up. Okay.
Yeah, and in terms of new product arriving to the platform, like do you use some features like visual features of the product, or do you only use like textual features provided by the very vendor?
Okay, so well, to be honest, we do take visual features. We have multiple feature sources. Usually we take the title, price, category, seller ID, or something like that. But we also have other embedding system. I think it was another presentation probably on other conference how we do that. But it's basically visual LLM embedding those and trying to get similar images together and different distance from each other.
Okay, I think this was last question. Bartosz, do you have more questions? No? If not, then this is your turn now. So let's thank Paweł once again. Thank you. And let's welcome our second speaker, Bartosz Naskręcki. Welcome.
All right, so thanks for the invitation, the place. Thanks to all of you for coming. So I'm going to talk about the apparently different topic, but I think we share with our previous speaker a lot, especially because the technology behind what I'm going to talk about is basically the same. I actually had the problem when I was preparing these slides because there is so much going on. Then like packing this up in one presentation will be very intense. Maybe some of you have heard that there are some new models coming, especially for reasoning in mathematics. So one of these models has now this official name, GPT-Sol. Should be released next week, probably on Thursday. So we are going to see if they will manage to deal with people from Pentagon and all this security issues they had. The model is really good, so that makes sense that they had to postpone it. I was actually using it for a while, and I can tell you a little bit later privately, like what I think about this model. Okay, but let me follow up with what I wanted to present for you today. Okay, so I will start just from advertising. You're not supposed to read at the moment, by the way, this stuff. Maybe I can zoom it in a little bit. So we wrote actually a little comment in Nature Physics last year. It was, I think, in August when we were drafting this paper with Ken Ono. And this is, so we were basically asked by the editors to say, what do you think about the future of mathematics in this modern era where artificial intelligence is clearly somehow starting to help mathematicians to work. And I think in August, we were pretty consistent that there's definitely something coming. And we even made a graph, which we can see actually in the paper. But we were thinking that really the process of going from informal mathematics, so the stuff that people really did for like lots of years, into this formal part where you actually replace mathematical artifacts with basically some kind of code that verifies it. And going further to something called auto-formalization, where you basically have a language model reading this code that it produced, understanding the errors and improving on that, and basically seeing some kind of machine assistance in the proof. So we were thinking in 2025 that this is something of the future, that this will maybe happen like around the year 2030, maybe later. And I'm really surprised that already this year, well, I was actually before the talk, I finished writing a full math paper, basically using this paradigm. And it took me like literally just a day to finish a project that I've been struggling with for like 4 years. So the acceleration is really happening. There might be like really a lot of disturbance in the coming weeks and years. Because it's not only about mathematicians, I think it's about scientists in general, about specialists, that if you have verified knowledge, you have some kind of verifier. That's actually very important. So maybe this is not something for philosophers, for artists, for people who are using actually knowledge in a different way. But definitely if you have this kind of hardcore knowledge that you can verify, I think this kind of amplification for humans is going to be really, really significant. So one of the reasons why I think it's going to be significant is because it's really cheap and efficient to train models for these kind of pipelines. Like if you have undistilled knowledge that requires some kind of evaluation which has no hard metrics, then it's very difficult to train a language model to somehow follow this kind of intuitive thinking. But in mathematics, especially, a lot of mathematics is done in a way where this kind of intuitive thinking is really at the beginning, but then there's like a lot of technical stuff that still takes a lot of time. It's very hard. And we are really seeing that this hard part is really going away. So like we can really use a lot of assistance from the models, which for me is really surprising because me as an active mathematician, I can really see that the models are really helping me with proving things. So like this question about the superhuman mathematician, I think it's still open. I mean, it's open in obvious sense that we have not seen any proof of any famous big conjecture like, you know, like millennium price problems, they are still completely open. And there is actually the phenomenon that any kind of system that kind of improves the pipeline might have like this long end, like there is this kind of law of diminishing returns that probably a lot of problems which are super hard might be really doable, but the amount of effort to, you know, scale up the infrastructure, maybe scale up actually the pipeline, the scaffolds and so on might be so intensive that we might still see that this long tail will be very long for many, many years. But that doesn't mean that, you know, like most of the stuff that we actually do on a regular basis when we are like experts in a domain is not going to be somehow conquered by the models themselves. And I'm not only talking about the LLM models, I'm really talking about different type of pipelines. There are some pipelines using completely different architectures like Mamba, but these are still not scaling up yet too much. But there are also architectures which are really mostly using some kind of, I would say, symbolic representation, and these kind of pipelines are actually also taking the lead in mathematics, and I think this is really quite impressive if you combine all of this together. So if you didn't have a chance to read this comment, I definitely recommend it. You might be actually smiling because like at some pages we make some kind of predictions like with some kind of perspective of like years. And if you look around, you're going to see, or if you summarize it with Claude, the Claude is going to point to you that like check, like most of these things have already happened. I remind you that we wrote it at the moment where Mathematical Olympiad was a thing, right? So Mathematical Olympiad was considered to be really hard. But nowadays, I ask like many people in the labs, they are not even interested in participating in Mathematical Olympiad because they consider it a solved task. So that shows you maybe a little bit the perspective of where are we actually going. Okay. So I've been also part of a project which was called Frontier Math. And this was an interesting project. So we basically gathered like 35, 40 mathematicians from around the world and basically met in Berkeley last year near San Francisco, just to talk about preparing basically 50 difficult problems, which had to end up with a number, but these were really like math papers. And the predictions were actually very bold. Like we were expecting, at least from the experience of using a model called O4 Mini, that was at the time the best model for doing mathematics, that these problems are going to last at least like for a few years, maybe not for a decade, but definitely for a few years. And I think at the beginning the predictions were pretty steady. So like when we released the benchmark in August, still like in the end of September, like just maybe like a few % of the problems were somehow tackled a little bit, but not something really spectacular. And I think at the beginning of this year, we have started seeing that. So this is like one example of such a problem. It was actually discarded because it was already too easy in 2025 for this O4 Mini model. So if you find this problem difficult, then I want to advertise that this problem was easy for the model. The only difficult part for the model was actually that it was not allowed at the time to actually compile the code in Sage. So it could not provide the final number, but it had all the ingredients, okay? And now if you actually look at the reasoning trace, which was still available at the time, you could really inspect it. You can really see that all the elements of the proof are there. So that means really it's a valid solution. Of course, there might be some corners which are a little bit off, but that was something that was already considered easy at that time. And trust me, but we had really 50 hard problems. And now I just checked the update from yesterday. Oh, by the way, in the meantime, we also designed, okay, maybe if the problems are not going to last too long because we have been seeing some progress, let's design some open problems. And these open problems were really actually open problems for mathematicians. Actually, one of these open problems is already solved, by the way. So someone actually used a scaffold that really solved this problem. I actually made a submission. So I'm really hopeful that if this problem will be solved, then it will be really great because it will be like a real progress in mathematics. And here's the update from yesterday. And it's going to actually increase, I can tell you the insider's knowledge. Next week, probably it will go to 95%, really. So this is the saturation of the benchmark. if you're curious, like how my problem is doing in this benchmark, so it was really for the first time, I think it was solved with GPT 5.4. But surprisingly, it was the only model and the only time that any model has solved it once. So it was like 11 runs, and in one run, it actually solved it, not completely, but actually just to give the solution. So I would say that my problem is still like one of these that is really consistently difficult. So it doesn't mean necessarily that this bar means that every model really solved every time, every problem, like if you look at the same level. But definitely we are getting to the level of saturation. And I would say that professional mathematicians, if they see the problem, they'll have to spend like at least weeks thinking about how to derive the solution. So we are really seeing substantial progress. You can ask many questions like, can you really train the models against this kind of problems? Like if you just see the content of the problem, can you anticipate like, oh, there are just 50 mathematicians, so let's train on like all of archive? Well, I mean, in principle, yes, but it's really difficult. I'm not sure if you ever tried to post-train a model against any field, any domain, but it's definitely very hard. And I would say that this is really showing you that the technical mastery of these models is actually going pretty fast, and it's accelerating, because if you look at these numbers, you can really see that the major of the progress happened like in the last 2 or 3 months. Okay, there is actually some reason. So like GPT 5.4 was actually post-trained in a new way. It was post-trained with a lot of synthetic reasoning data. That was actually, I think, one of the novelties of this model, and we could really see a lot of progress there. My personal opinion is that if you actually apply a scaffold to pure models, so these are like really tested against pure models, but if you build like a scaffold around GPT 5.3 already, then you should be getting like close to 70%. So like with these models in the top, I mean, if you make a scaffold, they are like already at the level of 100%. Okay, so like we don't have any new problems to offer. And I would say honestly that I don't find now any problem that I can solve myself and the problems and the models cannot. So like, and I don't know actually many mathematicians that can do this kind of tasks. There was actually an experiment last month called First Proof, that top mathematicians prepared something like a batch of 10 problems and gave everyone like a week. Just try to play with the problem and like use whatever scaffold you want. And actually 70% of these problems were solved by the end of the week, right? These were like really novel scientific problems. So I think we are living in a very interesting time that a lot of insights are going to become very cheap. And now you should prepare for this, because like if this kind of technical knowledge is becoming cheap, then the question is like you as, you know, people in the market, like how you should build your value. Like should I focus on some kind of arcane programming language? Probably not, because you know it's just docs, right? Should I connect different domains? But then the question is like, how far are these domains? Like, because maybe if you're connecting art with computer science, maybe it's worth the effort. But are you going to be really as good as in art and in computer science in programming? Or it's one of the domains going to be deficient? And then the question is like, can someone with a model that is trained for this domain is going to supplement your experience in connecting these domains? So there are a lot of questions that I think we should be asking, but definitely I would not put all my money, if you're like now building up your stack, like if you're doing it narrowly, I think this is not the path to go. But the question is like, then what kind of alternative we should make? Okay, this is just a reminder. Gary Tan actually wrote some funny comments about my problem. Unfortunately, I still cannot tell what exactly the problem was. I mean, like everyone looking at my papers can guess what kind of question that actually was, but we are still using it for the benchmark. Maybe at the end of the year, the problems will be really disclosed, but we are still testing Chinese models. We can actually see that Chinese models are maybe really good at general benchmarks, but they are not actually very good at this kind of benchmarks, because they are not post-trained to like very specialized mathematics. And that's something you should also keep in mind, that if you use open source models, then one of the issues with the open source models is they are not very much post-trained to any specialized domain. Okay, so like they are usually post-trained to like make a tick on the benchmarks, like all the standard benchmarks. But if you go a little bit beyond the benchmark, you can obviously see that a lot of things are not really working well. That also applies to other models, like commercial models are not also perfectly trained for any domain, but they are definitely investing more money into specializing them to like these highbrow benchmarks. Okay, so now I want to talk a little bit about the magic of the last 2 months. What is actually going on that it makes it so efficient that the models can really do formal mathematics? And I would say that the word that you should be paying attention to is called the loop. The loop is, well, it can be more complicated, but I just want to emphasize one very simple idea is that if you have a domain in which you can make a pipeline that like basically auto-validates itself, then and if you have a way to actually record like on a disk in a cloud some kind of insights from this research, then this is exactly the domain in which you should not be, I would say, spending too much time on, because there is a big chance that the models are going to get ridiculously good at this kind of domain. And in mathematics, the pipeline is actually particularly simple. So you get usually at the beginning, like after you prompt, you get some kind of AI slop that is generated by LLMs. That's a very typical output that you get. And you want to somehow change this AI slop into some kind of high quality code, which is really going to solve mathematical problems in a formal way. So I'm going to talk about this formal code in a second. And now the idea is that if you have this code, you try to see if it's going to consistently improve itself. And every time you see the errors and you see some kind of deficiency, you just document frantically everything that you see in this kind of pipeline documentation. And the important part is that you have a verified compiler. So you really have a proof that the compiler is not making errors, unless, you know, computers are like possessed by demons, but that's another story. But if you have a normal computer, that definitely is going to work. And then the compilation and the error feedback is exactly what it's training your pipeline to actually make less errors in the next round. So the point is that every time you use the LLM is going to make a lot of errors, but that's not the issue. The issue is that you stabilize all of these predictions exactly by deriving consequences. So like really jotting down all the instabilities in your code. Of course, this might not solve all of the problems. Like in many situations, this kind of pipeline might actually formalize for you the solution to a problem that you have not been even asking about. Okay, so that's like a completely separate story. But definitely this kind of pipeline is going to solve some problem. And the question is like, can you identify faithfully that the problem that you have solved was actually your own? Okay, so imagine a very simple situation that you're asking a model to like program a specific algorithm for sorting, and you have not specified what kind of algorithm you want to use, and then the model somehow decided that okay, like eliminating the elements from the list is a good idea because it simplifies the sort, and you end up with something called the Stalin sort, right? That you basically killed all the elements, right? I mean, you definitely solve the issue because you have not put any constraints, right? So that makes sense. You have formalized exactly what you have been asking about, except that you have not solved exactly probably the issue that you've been thinking about. So there's a lot of, I would say, ideation required to somehow stabilize this pipeline and making specs which are kind of stable to solving the problems that you've been thinking about. That's, I think, one of the most difficult stories of today. And the ideation issue, I think, is not solved at all. So like if you think that having this kind of pipeline is really a cure to everything, I would say it's actually not, because the problem of having solved different problems is another problem, and you need for this a supervisor model, and the supervisor model is still the same kind of pipeline. So why is it going to be smarter than the previous one? And you can keep on going in these levels. And it's still an open question. So in a sense, we are still at the beginning, but sometimes we luckily see that we are solving some problems, but it's not clear completely what kind of problems. Okay, so I want to talk a little bit about like how is it possible to magically turn mathematics, which you might remember from school, like a lot of obscure formulas, but like what it has to do with programming. So I want to advertise that actually mathematicians are very good at hiding this fact that mathematics is really programming. Okay, so if you have ever seen something like a proof is just literally something that you can compile. And the theorem is like a function that you want to compile. So this actually has been turned very precisely into a mathematical framework. So like if you see a question in mathematics, then you might think about this kind of situation that you have someone asking like, what is the densest packing of spheres in 3 dimensions? This was actually one of the most complicated theorems and proofs that was ever formalized by Thomas Hales. And it's about like 1 million lines of code, right? It's a very dense code, which exactly proves the conjecture. Of course, the process of formalizing it was really a pain. Nowadays, there's a lot of progress with AI, but it's still a pain, but it's a different type of pain. And here you actually, I just took like from this plethora of different automated theorem provers and programming languages that we use for mathematical proofs. I just took some. This one in the box is actually quite special because in Poland, we have a group in Białystok which is developing this programming language. It's called Mizar. It's a very nice language. And as you can see, like really the theorem is a function and the proof is something that you really try to compile. And what makes it work is something called type theory. It's like basically, like if you remember something called the implication from logic, like A implies B, then think about it as a pipeline. Like if you start from A, there is some kind of pipe that produces from this A produces a B, right? And in logic, we say it implies. And in this programming language, we just basically say that A is binded to B. And now if you combine an A with B with C and so on, you're just building functions. These are called lambda functions. So really, literally, a proof in mathematics is like combining all these pipes together. And like in the beginning, you have all the assumptions. So these are like all these A's. And then in the end, you have the conclusion. And the only problem is that you have to connect the pipes, right? So it sounds very easy. And I would claim that everything that you can prove in mathematics is exactly this, okay? Now the question that really remains is like, who is going to decide and in what way how to put another pipe, right? Like who is the plumber that is deciding, okay, I'm going to make a turn, I'm going to do some kind of divergence and so on. So I would say that the devil and the trick is actually in these details, because what the models are forced to do actually now with this kind of methodology in mathematics is to really try to decide which pipe I'm going to choose from, okay? And if you think about simple analogies like games like chess and Go, think that the number of possibilities of what you're supposed to do is very limited. In mathematics, like if you have a very simple proof in algebra, you might have like something like about 5,000 or 10,000 possibilities what you're going to do, and you can still choose different variables. So basically the possibilities are endless. So the question is like, is it really possible to train a language model to program mathematics in this particular way? Okay, so let me move on. So one of the most popular programming languages for doing this kind of formal mathematics is called Lean. It's just a derivative of many popular languages which are functional. So it's not some kind of dark magic. Its remarkable feature is that it's actually packing up a lot of steps into things called tactics. So that the tactic is, like a constructor that allows you to do like in one go, something like maybe 10,000 steps, okay? And these 10,000 steps are like things that you usually do with the axioms, so you never do this actually in real world. But if you want to really combine it into a proof artifact, you have to do them. So like physically, I have one slide showing you this. So here on the left, you have something that you might have heard about, like if you sum numbers from 1 to n, okay, so you can really read this statement. It's not very difficult to read it. Like for every integer n, if you take the sum of integers from 1 to n, okay? The sum of these integers is just n times n plus 1 over 2, okay? I just multiplied by 2 on the left here so that there is no fractions. It's really a statement about integers. And now the proof that you see in Lean before you compile is exactly just this very little snippet here. So you have a proof by induction like you did it in school, and you start from the verification for 0. This is just a simple simplification, which means you just verify the tautology. And then you have the induction step. So for the successor of n, so for n plus 1, right, you have to rewrite the left-hand side with the value, then rewrite again, and then you apply something called the ring tactic, which means basically you simplify your expression. But now, if you look at your like your notebook, how you actually did it is basically this kind of stuff. Except that now, if you formally write it down in these terms of axioms, you get this monster here. Okay, so now you should appreciate that mathematics in school was really hard because nobody told you that you're really doing all of this, right? I mean, maybe you have not been aware that you had to verify that every time you add, it's actually a commutative feature, right? And like 2 plus 3 equals 3 plus 2 is not something that is given, it's actually a theorem. And every time you do mathematics in this regime and you want to really be sure that it's going to compile, well, you have to put all the pipes, okay? So somehow the difficulty of turning mathematics into programming language is that we have to train the models to be very good at connecting these pipes exactly at this level. Well, you can cheat and you can somehow make the models into vibe coders, is that they feel, right? They feel they have to do the identity, okay? And that's exactly what is also happening. Like the models are being trained, exposed to papers that you can find on the web, and they are just feeling that they have to apply this specific tactic. There are more cunning ways of forcing the models to think, but to be honest, like what we see nowadays, so all this progress with frontier math is supported by basically this feeling on the left, not really hard coding the mathematics the rate on the right, but we are also getting there. So I think the future of the models, in my prediction, is going to be really scary, because if they really get very good at tinkering with math at this very basic level, they are going to really start inventing new things. The question will be like, is this stuff going to be understandable, right? I mean, like decompiling this stuff into something, like that you can explain is like trying to decompile the code from exe file to some kind of high-level Rust code, right? And I know examples that it's doable, but like in big scale, it's still a little bit out of scope. But we are also getting into this direction. Okay, so let me go further. So why we should care about this strange paradigm of doing formal mathematics? And it's not only for the fun of mathematicians who like to prove strange theorems. It's mostly for the industry. And this is like one of the big pushes why this formalization is a thing. So one of the examples of when this actually happened, it was actually in the 90s. A company called Intel had this lovely bug in the Pentium processors. It was called the FDiv bug. And this was actually detected by a mathematician who was doing some experiments with the twin prime conjecture and twin prime constant. And he noticed that something was wrong with his CPU because it was computing the wrong digit at like 7th or 8th position in the decimal places. He checked with his colleagues. They were getting consistently different results, but everyone who was using exactly the same architecture was getting exactly the same end result. So what turned out was actually happening is that Intel at that time was not using formal verification to verify that the floating point arithmetic architecture is correct. And they had to actually withdraw this CPU from the market, mostly for public reasons. They had to pay something like $500 million just to replace all these CPUs on the market. It was very expensive. And at that time, they decided already in the 90s that, there are these people in logic that are advertising this formal verification. Maybe we should try using this. And that was exactly one of the early beginnings of how the formalization started in the microprocessor world. So actually nowadays, if you're wondering like how is it possible that NVIDIA is shipping so fast new GPUs, that's exactly one of the reasons. They have like a separate lab where they are actually verifying, compiling their verification of every single circuit that they are running. So there is no chance that the circuits actually have any kind of logical bugs. They might have physical features that are like, you know, like a blob of, you know, silicon in the wrong place, but they don't have actually logical bugs. The other place where the formal verification is becoming a very important topic is all sorts of cryptographic protocols. So one of the latest is actually a project which was started with Signal. So Signal has this very nice cryptographic stack, and now they are actually formalizing exactly whether the whole stack is provably correct. Okay, Amazon is using this. A lot of organizations are basically verifying their pipelines, especially if they are like doing something on production. What kind of tools you use there? Well, there's like usually custom-made tools. So these are not like things like Lean or Isabelle or Coq, but basically the same principle applies. So like every time you have a production code, the production code is in parallel mirrored by the formalizing code, which is being compiled at the same time as the production code. And the formal code is verifying that the specs, the assumptions of the code that you're supposed to produce something specific is actually really working. So like the companies are really making efforts to formalize whatever they do. And I think one of the biggest examples is exactly in Amazon when they have these delivery centers, like everything in the logistics is actually being proved to be correct. And actually the guy who invented Lean, Leonardo de Mura, is working for Amazon. So he is actually developing completely new pipelines for verification. So if you're interested, then I can give you some more interesting references. So probably one of the skills of the future will be exactly this kind of stuff, like becoming a proficient, verifier for whatever processes are important in business or in industry. Okay, like people want to make sure that the money is going to come, right? And you have to prove it, right? And then you use this kind of formal ways of making sure that you're going to make more and more money. Of course, it's more complicated, but one aspect is really being sure that what you have programmed is actually completely correct. What's interesting is that out-of-the-box models like Claude Code can actually do a lot of these formalizations by themselves already. That's quite impressive. So again, if you think about your skills, maybe not necessarily doing exactly what Claude does, but inventing new formalizing protocols, that's definitely something that is very interesting. But there are not many programmers that are like compiler designers. Usually people use compilers, not design compilers. But that's definitely something that is going to be very, very popular. Okay, here's another project. It's called Cedar. It's with AWS. And I could talk a little bit more about this, but basically the idea is that it's really giving proofs of design properties, and it's actually quite a complicated stack. Most of the code is actually written in Rust, so you don't need like a specialized compiler. You can actually do this stuff in Rust. There is also a little bit of Lean, so that's kind of a mix of different things. Okay, Eneas is another project. It's also featuring Rust, actually bridging Rust and Lean. We actually have people in Poland, Professor Dziembowski and his group. They are exactly doing this kind of stuff. So if you're close to Ideas Institute, maybe you should drop him a line because he's really doing a lot of cool stuff in this area. Okay. Well, I already talked about this pipeline in mathematics. So this has been already in the wild for a while, and we are really seeing that this chain of thought and this kind of like improving infrastructure proof writing can be really done in a very efficient way. So I think one of the early successes was this project called Lean Dojo. Another one which was much more specialized was called Alpha Geometry. That was actually a very small language model that was just trained to do proofs in Euclidean geometry. I think I have one example, or maybe not. I just removed it. I think it wasn't too much time for that. Well, and basically the same kind of pipeline is like used in the background for training regular models to do like mathematical Olympiad, programming Olympiad. What is maybe a little bit different for these models is that they are not necessarily trained with Lean only, but they are trained with symbolic Python. That's one of the features of the latest models, that they are able to actually program symbolic Python, and they can actually do a lot of computer algebra assisted reasoning exactly with this kind of general framework. So if you actually know a little bit about how symbolic Python actually works, then you can use the same kind of approach to structure up reasoning models that are much more consistent in the outputs than just regular LLMs. Okay, so this big name in this year is actually called large reasoning models. Well, reasoning really means here that they stabilize the inference at test time compute with exactly producing some kind of verifiable code. And you can ask a question like is this a sustainable environment? Like are we going to see that this will really scale up to the full-fledged reasoning? I think the answer is we have no idea. I mean, like we really see that every time there is some kind of obstacle, people are thinking like, oh, maybe topology is a thing that nobody will be able to do topology. Then you realize that you can actually train topology in a different framework, which is textual, and then you have a win-win, right? And I have not seen in the last 2 months any domain of mathematics in which there was no progress with this kind of paradigm, mostly supported by coding. But I would say that somehow the frontier is going to definitely go much faster than we expect. And the ceiling is probably still very, very, very far. Well, there are many strategies to do this post-training. One of the early ones is a process reward model. And this was actually one of the textbook examples from 24 for how to train the model on like very simple reasoning schemes. Now these new reinforcement learning strategies are actually not disclosed. So if you ask people from the labs like OpenAI, they're not going to tell you exactly which reasoning path they are actually training, what kind of technique they are doing. Most of these things are not in the conferences anymore. So that's also quite interesting that a lot of these new models are being trained with the ideas that are not completely disclosed. Of course, they are becoming much more expensive to do, but I think we are going to probably see these techniques maybe in a few years, but then it will be definitely different. Okay, so I already talked about generating mathematics as code, but you can also do a lot of mix, like you can mix up, that's something that Google DeepMind is doing a lot, like you can mix up this formal reasoning with genetic programming, and if you combine this or like some kind of, like genetic algorithms, you can really see that the frontier is pushing much faster. So here you actually have examples of problems that were actually improved by their models. Unfortunately, some of these models are not available yet. Like I think Alpha Evolved was not disclosed. I mean, like Google is very careful about like what they are disclosing. They probably are training their Gemini models on Alpha Evolve. But definitely they were proving completely new insights in mathematics. Not maybe something shockingly new, but definitely improving on optimization problems. And that's something that I think is quite significant for these new models, that they are very good at optimizing and auto research. So that's something definitely new. There are also new models which are like bundles, like across domains. These are usually called like co-scientists, AI scientists. I think the latest addition here is by Sakana. They actually trained a new model which is called Fugu, and it's still not available without VPN, but it's actually very good. And the reason that you train these kind of models is that you want to have this kind of cross-disciplinary experts. And again, the pipeline is, I would say, very similar to what we have seen so far, is that you have a little bit of domain knowledge, a little bit of formal thinking. You really have to, I mean, even if you're a biologist, you have to think logically about what you're adding to the bottles, right? And then this logical reasoning is stabilizing what the model is actually suggesting. And, like if you're making a vial of something that will be, a vaccine instead of a poison, well, you have some predicates that allow you to check this. And if you put everything on the table, you can really see that this is essentially a reasoning problem, right? And a reasoning problem is basically something you can apply a resolution to. So again, you have a pipeline which is training basically mathematics with a little bit of domain knowledge to make this new kind of discoveries. These models are typically very expensive. So if you build this kind of harness, well, you should be really wealthy with tokens, because really making a stable predictive model that can stably reason with logic, well, that's something that goes into billions of tokens. So in my recent 2 weeks, I've been training auto research pipelines, quite successful for like some of the new algorithms. Like one was actually some quantum algorithm for breaking Ethereum. And at the end of the 2 weeks with these auto loops and all these stabilizations, I checked like how many tokens I've burned, and it was like about 20 billion, right? For 6 projects. So now you can see like the scale, like it comes at a cost, but sometimes the cost is worth it. And of course, there is a lot of people trying to somehow build and optimize these pipelines at a lower cost. So again, this is something that might be a job of the future, like how to make a pipeline that is at the same time cheap and stable and reliable, right? That's something that still nobody knows how to do, and especially the companies with a big AI stack, they are not very interested in lowering the number of tokens. They are interested in pushing the boundary, but like most people would definitely like some kind of mid-tier, right? Like you don't have to spend like $500,000 to solve one issue. Maybe if you spend like $5,000, that's okay, right? And the question is like, what kind of models you should put into the training? Like, should they use the maximum reasoning effort, but that might be too expensive? If the reasoning effort is too low, then the logic will be not consistent, and then in this loop, you'll be just basically making turns without any progress in your formal reasoning. Okay, so just to finish, I want to highlight a few very interesting companies. So one is called Harmonic. They actually have the closest bureau they have is in London. And if you want to work with them, I definitely can get you in touch with these people. They are very nice. They are actually building a mathematical, well, they call it mathematical superintelligence, but what they are actually building is a language model that can natively reason in Lean. So that's different compared to the other languages. And they are really doing a lot of very good progress. They are applying this already in the companies with very good results. And they have very interesting stack. So if you're interested, I can tell you a little bit more later. Kimina Prover, that's another, I think, very promising story. It's like the idea to build an open weight model in which it can formally reason. You could use it even for your own code, and you have some kind of control. So you can post-train it. You can somehow change the way the model works. So it's like if you go to Hugging Face, you're going to see a few models like this. They are completely open sourced. Of course, the training set is not open source, but at least you can use the model completely openly. Well, there are some projects with bigger companies which are mostly targeted at mathematics, but they are mostly for show. So I would say that like if you look at mathematical highlights, it's not the place where you should be looking for the job, but definitely you should be looking for the frontier. So the frontier is like 2 months ago, this company called Math Inc. They were actually using Claude, by the way. They basically finished like a full formal proof of mathematics of about like 500,000 lines of code. That's comparable to what I showed you that took 15 years for Thomas Hales to do by himself. And this project was actually finished in 3 weeks. I actually made a slightly different project, which is, well, a little bit smaller. In my case, it was like the final version of the code is like 10,000 lines. And I did it like within a week. Okay, so the progress is really increasing. What makes the difference is like what kind of harness are you building around your base model, and there's a lot of interesting stuff you can do really there. Okay, well, you probably have seen some stories about Erdős problems. I would say they are all honest. So really, these were really open problems in mathematics that were solved with models. But one thing I want to say as a grain of salt is that basically these problems were so obscure that literally no mathematicians cared. I mean, like no one for the last 50 years ever cared to look at this specific problem. And the reason it was not solved was not that it was like extremely hard. It was like Erdős was producing a paper every week. And, you know, like there are like, I don't know, like 5,000 people working in combinatorics in the whole world nowadays, and there were less in the 70s. So like 50 people who were peers of Erdős, they didn't have time to look at all the ideas that Erdős left over, right? So these are like really crumbles in the street. And eventually, you know, someone said like, okay, we have now this cool programming models. Let's try it as a benchmark to see like how much progress has been done. So if you think that this is a huge progress, I would say it is kind of a progress, but mostly it's, you know, like on the side of showing the capacity of basically solving not extremely complicated math problems. Like the amount of mathematics here to solve these problems, or like compared to business, like Aeneas, for example, I would say it's a tiny fraction, okay? Okay, these are sometimes really interesting things, like even OpenAI recently advertised one of these problems. Let's be honest, this is mostly for show. Okay, here's one slide from my collection, and it's exactly the same kind of experience. Like I was testing like very early GPT, I think 5.1 or 5.2. Like how capable is it? Like I give it a task, like there is some kind of problem. Like can you actually give me the AI slope? And then the Aristotle from Harmonic was able to formalize it, and it was done. Okay, but it really showed me that mathematics is really much easier than many people think. And the question is then why people care about doing mathematics? Because the difficulty is not in solving these kind of horribly looking problems, it's actually in designing them. Okay, so the most difficult part of actually being a mathematician is like how to formulate specific insights in this mathematical framework that will actually make any sense. And now you can see with these models that really the proof generation is becoming cheap. But what's still very difficult and hard is the ideation, right? Like how you can organize things, like define exactly what is important and then make it run. And I would say that the current models are still not very good at this. Okay, they are very good at this technical level, but not maybe at this final step, which is like the highest level of ideation. Okay, thank you very much.
Okay, questions.
Hey. Good job on making those predictions in the Nature comment paper. I have a business proposition involving lottery, if you would be interested.
We should talk about this.
Cool. In all seriousness, I was wondering, you know, when an LLM is solving those mathematical proofs, there is a logical part to it, you know, expressed in symbols. And then there is also maybe a part of abstraction when you said about the intuition.
Yeah.
And as we have seen, there seems to be fewer and fewer mathematical problems that are still unsolved. I was wondering if there are counterparts to it that don't involve mathematics. I'm thinking riddles, like, you know, there is sheep, wolf, a cabbage, and you pass the water on a boat. So we still effectively use the same skills, but not in the symbols of mathematics. So do you have an intuition for how good the models are in those kind of tasks?
Yeah, they're absolutely perfect, but not in the way that Andrzej Dragan is using them. So like Andrzej is usually asking this riddle to like vanilla LLM, and vanilla LLM is, you know, like basically building a vibe, right? And the vibe is just, you know, like a text based on the pre-training. So like in every example that you have a sheep and the wolf and whatever, they go through the river, right? But that's not the point. Like the point is that if you turn, for example, I know like GPT Pro or Claude Code with Opus or whatever, then you can really see that at the background, the reasoning, what is happening is that the model is trying to translate the problem into some kind of formal logical scaffold. Like he's really writing Python code that is trying to, you know, like build this kind of, sometimes you can even see that the model is really trying to invent functional programming with Python, which is quite impressive. And it's building, you know, like some kind of, you know, situation picture for how to solve it. But I would say that like for reasoning models, even this kind of problem might take like at least 2 or 3 minutes to completely code up everything. And well, usually the reasoning traces are not disclosed, but if you look at DeepSeek, you can actually see that the number of reasoning tokens and the actual situation that is generated by the LLM goes into something like, it could be like 5,000 tokens or maybe more, right? So somehow the magic of stabilizing and doing the real logic with this kind of questions is like how much you invest in test time compute. And there's absolutely no magic in this. If you put the lever to the right and you allow the model to reason longer, okay, there's a cap at which it saturates, but basically there's like a big difference. If you have like vanilla LLM, even with chain of thought, the difference between the model that is actually building up its own code, it's producing all of this reason, it could be like, a fraction of 1 to 100 in terms of the number of tokens produced, but also the difference that it's making is that the code produced with these reasoning models is actually being compiled. And when something is wrong about the situation, like like you put some strange precondition, then you can see that the model is actually doing this kind of, there's something called Vampire. It's like a software for verifying logical predictions, like some kind of, logical envelope production. And when something will be wrong with this kind of setup, the model will see from the compilation that it was wrong. But it's not the LLM that is doing the thinking. It's actually the compiler giving the feedback back to the LLM. And if you have this feedback loop, which really happens in big LLMs which are doing the reasoning, it takes time, but it's completely stabilizing the logic. So somehow I would say that if you turn off the reasoning, even the best models at the market with trillions of parameters are still completely dumb about anything that goes beyond like very tricky, simple setups that are like completely predictable. Okay, so really what makes a difference is exactly this part that once you turn on programming into model, it can actually do formal reasoning at completely full general scope.
What do you mean the code is compiled in the reasoning step?
Well, the
output is compiled, and then we have
the output is compiled.
Okay.
Yeah, the output. So all these servers that run these cloud models, they are actually compiling this code. They are actually doing this. And if you have like your offline model and you don't allow the model to compile it, even if you have reasoning model, it's completely useless, right? Because it's just like producing garbage, but with no way of improving. And another reason that these new models are so good is like you build, like a knowledge base in which every kind of error is actually being documented in this kind of tree-like structure, and this is giving you also a tremendous speed up. So like I showed you this example with Math Inc. They were using just vanilla Opus 4.7. That was a stupid model. That was absolutely a horrific, stupid model in terms of mathematical reasoning, but they did only one very interesting thing. They built a repo on GitHub called OpenGauss, which was basically a targeted scaffold. Like every time Opus was producing this AI slop, it was actually a lot of engineering used for trimming this code, just re-recording the interesting ideas from that, and then prompting back the Claude with these insights. And it was self-improving thing.
Awesome, like consciousness.
Yeah. That kind of feels like really. I'm not sure if consciousness is the right word, but definitely it's reasoning with memory, and memory can be unconstrained. If you have terabytes of hard drive, that's cool. Maybe it will be slow, but definitely it will be consistent. Yeah.
All right.
I have a question that, first of all, I have to warn you that this would be a stupid question, but...
There are no stupid questions. Maybe I'll stupidly answer.
Okay. But basically, if we have like such a person here, I have to ask. Because you're solving mathematics, and basically, you were also like talking about programming and how like people should position themselves if they should do programming or they should do art, like mix or something, because the programming will be solved. And I have a question about like solving finance, for example. And let's assume that we have a like multi-billion-dollar company and a fund, and basically there is like the deal flow that those funds are buying stuff, like for example Hilton, Marriott, Adidas, like huge thing. And basically it works in a way that there is a deal team, and deal team is like getting all the information about the company, and basically there are senior managing director who are taking all those stuff and are like seeing finance, I mean like the balance sheet, cash flow, and so on. And they need to have like sensitivity. They could figure it out that, for example, I know there is like the specific points at the like balance sheet which are not right. Basically, we have to like subtract the specific amount. We have to add it or something. There are like other stuff which is like, for example, they are thinking that there is a specific disruption in the specific part of the world, so we can't buy it. There are like the other stuff which, for example, we have to think that basically there is specific management and there is like higher probability of them going away because basically they didn't get enough equity or something like that. I mean, when you just talk with all those people, you know that it's extremely complex, but it's finite in a way that there are probably 2,000 things that they are, talking about. And here's the question. If you think that basically right now we are close to solving finance, which means like we are getting all those information and basically we could just think about this deal in the 2,000 planes or 3,000 planes. And if I'm saying right now that LLMs are thinking math, this shouldn't be a problem if we should think about like on 3,000 planes and figure it out if the investment is good or not. It could be complex, sorry, but once again, I just had to ask.
Well, I can say, I mean, there are like a lot of fintechs. I actually was contacted recently by one. They are really small companies, usually startups, and they are actually now thinking seriously about using all this formal reasoning plus reasoning LLMs to somehow take care of all this complexity of the process. So one thing which I can tell you is that definitely, like if you look at some of the best funds, like Renaissance Fund is probably one of the best, maybe Medallion is the other. Like if you look at who are the people who work for them, okay, or like Jane Street recently also, I mean, they are hiring top mathematicians and top coders exactly for this purpose. And like what will happen in like the coming years, I think like the economy, of course, it's like, it's like a connected vessel, like everything should be in balance. That's something we know, right? So if anyone is going to make a little progress, I think basically you're going to see that all the accidental investors are going to stop getting any margins. Like all these companies now are thinking about doing like microsecond improvements, like D-Show, and there is like a lot of these companies that they completely switched from like classical quant. Like quant was like really a good mathematician, statistician, but now they are empowering these quants with actually very nice predicting models. They are building also simulations with, like general economy, some geopolitics. That's maybe the most difficult part. Like can you predict what Donald Trump is going to say tomorrow, right? That's probably one of the most complex variables that you could try to estimate. But surprisingly, like if hire people from like psychology background, they might give you some insights. And like if you really think about a lot of things that we do, like you don't go every day to the metro in Warsaw, for example, right? Then like you could see that like there are a lot of patterns that are not obviously visible for the participants, but they can be modeled. And if they can be modeled and streamlined, you can make this is called like monadic programming. Like in monadic programming, everything that is a side effect is taken into account in the monad framework, and basically like everything becomes functional programming. So if you're really obsessed with somehow control and like building really sealed systems, then monadic programming and exactly what I showed you before is exactly the framework which allows you to take into account all these side effects. Of course, there is like real world, like with real variables, but still you can make estimates for the errors. And like there are really very few places where the errors are completely unpredictable. Like in Poznań, we have this team at our faculty that is working with this team Lech, Poznań football team. And they say that the most unpredictable aspect of modeling the football players is when they fall in love, because like, it's a catastrophe. You have no idea what is going to happen with the physiology of this guy, right? So like this is one of the very few instances when they cannot tell what will happen in the next match. Apart from that, everything is completely predictable. So like we have seen actually that we are going to win the championship like 5 or 6 matches ahead of the schedule because it was a very sealed programming. Of course, they were losing a little bit of reasoning part, but fintechs are actually doing this a lot. So you're on a very good track. And you should be paying at the Medallion Renaissance, that's definitely, but in London, there are also startups that are advertising. Usually they are in stealth. So if you're looking for the job adverts, you should be looking for some strange combination like formal reasoning and finance. And that kind of sounds off, but that's exactly this kind of good job.
Really great answer. So last question, like really quickly. So when you would approach such problem, let's assume that we have to build this, you know, so like what would be your first step? Like most probably I'll just check those companies, but in terms of
to look for this kind of job?
No, just creating such thing.
Well,
you know?
definitely you should start from the existing models. Like you have a lot of existing models on the market, but to actually make improvements, you should take into account geopolitics, and that's actually the state of the art what people are thinking about. Like how you can take into account that, you know, like China is changing the one-child policy, and like how do you build a neural network that is going to predict in like 5 years like what will be the gross product based on this? You basically build simulations. That's I mean, people from background in physics are doing a lot of this stuff recently. So it's like there's a lot of ingredients in the stack, but I would say that the geopolitics is one of the top topics for this kind of fintechs.
Cool, thanks.
So I wanted to go back to mathematics a bit, and at the end of your presentation, you said that the hard part of mathematicians' work is asking the right questions, and AI is not really good at it at the moment. So I wanted to ask, what is your prediction? Is AI not good at asking the right questions right now, but it will be great at it in 2 years? Or is it somehow a place where humanity can survive? How would you even train a model to ask the right questions, right? Because right now, for example, I think in Lean, there's this problem that if you generate like 2 million lines of Lean code that verifies a proof for a problem, a lot of mathematicians that work in Lean will tell you that it's not useful for them because they are formalizing problems in Lean for all those abstractions that are developed in the process. And do you have an intuition about how is this branch going to evolve?
Yeah, so definitely thanks for this question, because this is, I think, the thing. Like if you really look at this whole stack, I would say this is the only part of the stack that is absolutely, I mean, models are terrible at this, completely terrible. I have some ideas. Like one of the ideas that, and you can see it in the best conferences, is like people are experimenting with latent reasoning. So like basically in the transformer, usually the paradigm is that you project into tokens, right? But we have seen these examples. Like there was this famous recent example, like someone asking about the emoji of a seahorse, right? And there's no seahorse emoji. So the model was torn, right? Because it was trying to project onto things which are close, but they were not exactly the idea that he understood, right? And one of the, and this is somehow the suggestion that if you have an intuition that's kind of a thought, there is like a superposition of ideas that maybe you can already express, right? And most people actually have completely different types of intuitions. But if you look at these primitive architectures called transformers, you can kind of emulate intuition in the latent space, okay? And you can make, there's like a project, I think it's called Coconut, where you make a modified transformer, which like for many epochs is actually reasoning just with the latent space vectors. At the very late stage, it's actually projecting onto something concrete. And there are experiments where people are trying to somehow see if the intuition can be modeled, like maybe, like on parallel networks, doing exactly this kind of latent reasoning, and like somehow pushing away the moment that you are going to project onto something concrete. So I think this is probably one of the closest to having an intuition. But to be honest, I think one of the major problems with intuition is that we absolutely lack any kind of data set, right? Like how would you even start training a model for, you know, like an intuition that someone might have with automorphic forms, right? I can tell you, like, I can show you at least 50 people in the world that you could talk to them for hours, right? And then you can record all of this stuff that they said, except that you have not been recording what was the internal state of what they were thinking about, right? So I think one of the major issues with I'm not saying that it's impossible to train intuition. I think we have no idea how to approach this problem because it's even foreign to us. I think there's absolutely no research in neurosciences that will exactly tell you how the thoughts are actually generated on this, you know, like level of cells. We have seen evidence that there is some kind of activity in this part of the brain, right? But we cannot definitely say like how, you know, like high structured mathematical ideas are formed in our brains. So I think probably is research of the future. I definitely don't think nowadays that it's impossible. I think it's just complicated. Maybe the architecture is not correct yet, but I think it's not something that is impossible to do. I mean, if you can do it in the electricity of the brain, right? Let's say for the religion and, you know, like all the quantum stuff, that's out of context. But like, if you really think about what we know about neurons now, I mean, it's just a very complicated dynamical system with, you know, like all the parameters that can be in principle measured. So why we could not make a very strange architecture that would basically do the same? It might be very expensive. Like remember that your brain was basically formed by evolution, right? So it took really a lot of energy to get to this point that we see all these brains here, right? So it wasn't definitely a cheap process, right? And we have no idea how to make the architecture. I think this is probably one of the biggest problems. So probably in the NeurIPS of 2050, people still will be talking about how to encode intuitions, but maybe we'll be already past that. But definitely that's something that LLMs are terrible at. And if you actually let them run for in the wild, you actually see that, you know, like the ideas that they come up with are like, I mean, they are usually very unstructured. And I think this is one of the symptoms of using LLMs, that if you make the auto research loop and there is no human steering, there's like, you know, no imperative, then you just see wild things. I have one project I can show you that it's about cellular automata that I deliberately let it run for like, you know, 2 days. And then I started reading this and I said like, wow, everything was completely formally correct, right? But I had no idea what I was looking at. It was like, you know, like the property something had some kind of implication. And then I said like I cannot connect it to any idea I have in my brain. It was like completely external. So this can still be useful, but I think without structured guidance, structured intuition built into the LLMs, I think they are not going to scale up for this kind of problems. So that's definitely one of the challenges of the future. Very interesting one, yeah.
Thanks.
Thanks.
All right, and the last question, okay? If there are more questions, you can ask during the after party, because I believe that some people are hungry already.
Yeah. Thank you very much for your speech. Can I have a couple of questions as an ML engineer, like more specific technical questions to you about?
Maybe I should ask you more then.
Oh, no way. Well, my expertise is limited to one video that I watched on YouTube, basically about the solving mathematical problems. And out there, like basically you confirm that, you know, reasoning and proving mathematical theorems is actually algorithmical task, which is well, actually, it can involve LLMs, but it doesn't require it. It can be made automatically with Lean. And when I saw that video, there was an architecture that also required the auxiliary structures, because sometimes to prove some theorem, like, okay, we've already formalized the mathematical problem. I mean, the problem from the real world. We turned it into a Lean code, let's say, and yeah, for proving of some theorems, we need to get some things out of the blue, you know, and yeah, using those things, we can then sequentially go step by step and prove some theorem. And in terms of the architecture used by your research or by your tests, what is the exact role of the LLM? Is it like also providing the auxiliary structures, or does it supervise all of the process end to end?
So that depends. If you're like using Claude, right? Like Claude is really just literally just producing new tactics and compiling it on the way and checking like what is the proof term that you're actually able to prove. But there are actually different techniques also. Like maybe you remember that AlphaZero and AlphaGo were actually trained with this Monte Carlo search, and there were like different heuristics. So you can actually do the same with math. Like you could try to build heuristics like classical ML, right? Which are capable of telling you like what kind of step you're supposed to do at the moment. And I would say that LLMs are actually very good, like if you have to connect two different domains of mathematics and it's like a translation problem, like you have to transpose something from algebra to maybe combinatorics. And it's very difficult to like do the transposition with Monte Carlo. But for example, Harmonic is using also this kind of techniques. So they are like building models which are also doing like classical ML evaluation. But there's no clear, I would say, answer yet, like which strategy is better for the specific domain. I mean, like mathematics is basically like making these decisions, like which tactic to apply at a particular step. It's like you're trying to imagine you have like a complicated space in which you're trying to find the path from one place to another. And if you have learned that like a lot of places have like right turns, then you expect that if you have this kind of shape, it's going to be like full right turn, so you can apply it. And for example, alpha geometry was exactly trained in this way. They basically trained the model on something like 100 million synthetically generated proof steps of proof theorems. And they managed to somehow overcome the brute force level. So that was already quite impressive. But you can really see that this was not, I would say, strategy that would require some kind of planning for like 50 steps ahead. It was mostly like finding an optimal shape to get to the solution. And with geometry, there is something very specific, because geometry is an area where we know that the algorithm is decidable. So every question about planar geometry, you have an algorithm with actually predictable time frame that will tell you the answer yes or no. There is some kind of elimination algorithm for this. So I would say that geometry is very specific, and if you train the model in this kind of very classical paradigm, you can surely see that there is progress here. But there are domains of mathematics like group theory that we know that general problems are completely undecidable, okay? And here comes the challenge, because now if you train any kind of Monte Carlo or you train a very simple LLM, you can see that they are doing very well on particular types of problems until some specific level of complexity when they come to a deadlock. And we can actually see in a lot of examples that even the current state LLMs are very good at solving problems that we give them, because we usually ask them limited number of tokens in the problem, and there is some kind of like comparison between complexity and the length of the question. So maybe the worst case is like Fermat's last theorem, which is like 70 tokens, and the answer is like 300 pages, right? So that gives you somehow the idea like how complicated the answer can be compared to the question. But in general, I would say that like at the moment we see that there is some correlation when you train the model on I would say more and more complex reasoning, or like do this Monte Carlo heuristics, you are going to get really with involved problems, but I think it's not going to scale up indefinitely. So there is definitely a lot of discussion in the ML community, like, is it really possible with the current technologies, classical and LLMs, to really build this kind of reasoning with external database and so on? I would say we have no idea. We have no idea because, I mean, even if you think about people are also limited, right? So there is definitely the shortest sentence, which is provable, which no human will be ever able to prove, because the shortest proof is so long that it's like going past any possible lifetime of a human, right? So even humans are humbled and are limited. But the question is like what is the proportion? I think still people have I would say, much more shortcuts. And we actually have no idea where these shortcuts are coming from. I think this is related to this previous discussion about intuition. Is like building new heuristics, new tactics is something that people are very good at. LLMs are definitely not good at writing these meta programs, these heuristics. But definitely, if you have a problem in, like very constrained combinatorics, very constrained even abstract algebra, which only requires, substitutional logic and just some kind of very simple thinking. I mean, classical ML plus LLMs, which can jump from one translation to another, that's okay. But I think it's an open question, like how long it's going to scale up. My bet is that actually it's going to surpass people anyways, because it's just faster and more efficient. But it will be still dumb in the end. So I think it's a metaphysical question that you're really asking, are we really having some godlike features that we will be ever able to, design new stuff? I don't know, but definitely you can train models to become much more proficient than people at short reasonings. And short, I mean up to few hundred pages.
Okay, thank you. Last follow-up. So can we imagine this whole pipeline as an LLM acts like an agent and just fires up several lean solvers and
absolutely. I can show you on my computer. I have this kind of pipelines all the time. It's really cool, actually.
Yeah. Okay. Yeah. Thank you very much.
Thank you.
Yeah. Thank you once again.
Okay, thank you. So that was the last question. As I said, if there are more questions, you can ask during the after party, because we have to start the after party soon. We'll have time until 9 p.m. more or less, plus epsilon. Plus epsilon, small epsilon. Okay. Bartosz, thank you once again. That was a great presentation. Thanks for answering all the questions. And before we start eating sushi from the fridge, I would like to invite Piotr here, and he will tell about the gifts that we would like to give you.
Yeah, thank you so much for being here. This is the last event of Paweł's activity in this academic year 2025-26. Yes, so thank you for being here, and we have some special gifts for you for your presence here. So just please, in a while, come closer here. We will give you something. If it will be not sufficient for you, don't worry. At the end, you will find some more gifts. So yeah, thank you for being here. Yeah.
Thank you. All right, so Piotr will just bring some gifts now, okay? Do you need help? Okay, you'll manage. Okay, so we can finish the official part. So, and now we'll start unofficial part. So after party, you can take food from the fridge, and Piotr will give some gifts. Thank you, thanks everyone. Thanks.